Welcome back, guys. Today we're going to be solving all of chi-square tests, and how we do this is by evaluating the notes that I've made. These cover about 99% of every single question that comes in for chi-square test, and there are four types that particularly come, where there are tables, binomial distribution, Poisson distribution, and probability density functions. So these four types, if you just solve them by learning these notes, you're pretty much good to go for the exam. So let's begin. So the first type, tables. So first of all, they give us data values and then they give us rows and columns. So the first step is to state the hypothesis, which states the data, okay, and you don't need to specify data. Actually, you just need to say data is independent of the condition. In the above question, without even reading it, I can already say that the condition here is whether the data is independent or dependent on background music. And yeah, that's the condition. Step 2, calculate the row total and the column total. So I've done that right now, and what this value over here means is called the grand total. I'm going to represent that as GT, and that's equal to 350, which is basically the sum of all the values here, which can be calculated by actually summing them up, or it can be calculated by just adding up the row or column totals together. Okay, now step 3, label the observed values. So we call them, we can first of all set these values as O1, O2, O3, O4, O5 and O6. So let's say that I'm going to label the values. So let's say this is 1. I'm going to call this O1. O1. This will be O2. This is O3, O4, O5, and finally O6. O representing observed value, and 1, 2, 3, 4, 5, 6 is just a label. So we do this for each value, right? And we label them OI, where I represents the number assigned to the value. Now step 4 is to calculate the expected values. How do we do this? It's very simple. So what we need to do is calculate the corresponding row total and the column total, and then we multiply them together and divide them with the grand total. That is how we solve this. So in our example here, if we wanted to calculate the test statistic of 51, firstly our row total would mean 140. So 140, let's pull this up on the calculator actually. So let's say 140, which is our row total, times it by the column total of 51, which is 119, and then we divide it with the grand total, which is 350. So that means that the expected value of this 51 is actually 47.6. We repeat this calculation for each and every single one of them, and then we'll be getting 6 sets of expected values. Okay, so the E corresponds to the value expected. So in this case, if I calculated E, this would be named as E1. This would be called E2, and so on. So let's just label them E3, E4, E5 and E6. So we had to calculate each observed value, which is already stated, and the expected value, which is just using the formula row total times column total divided by the grand total. Okay, to finally calculate the test statistic. This is extremely simple. Once we've calculated our expected value, we use the most common formula used in all chi-square tests. And once you use these, for example, let's say that we got our expected value for this one, 51. Let's use the 51 as an example. So our observed value here, let's put it as 51 minus our expected value, which was 47.6, and we need to whole square this difference and divide it with the expected value 47.6. okay, and that gives us this value 0.2428571, some of which is recurring. This is the value that we obtain. Now we do this and we add them up with the same calculation we've done for each one of these, 1, 2, 3, 4, 5, 6, 7. So for all these 6 values, we perform this calculation and sum them all up. We're going to get a test statistic, right? So find the difference between the observed and expected for each given value, and then square that difference divided by the expected value. Finally, to calculate the critical value, it's extremely simple for table wise questions, because there are only 3 columns, 2 rows, where we have a total of 6 data sets. So how we perform this calculation is by doing r minus 1 times c minus 1, and that represents the degree of freedom. R represents the number of rows, c represents the number of columns. So the number of rows here is 1 2, so 2 minus 1, and we multiply that with number of columns minus 1. Number of columns is 1 2 3, so 3 minus 1, and this gives us our degree of freedom as 2. So it's really simple, where nu is 2. Now we calculated our degree of freedom. The other thing that we need to calculate the degree of freedom, to calculate the critical value, would mean to calculate the p-values. To get the p-values, we need to do 1 minus alpha, where alpha will be stated in your question. And yeah, you'll be able to get by finding the intersection of the p and v in the chi-square distribution. This is called your critical value. And final step would be to compare and conclude, so whether the test statistic is greater or lesser than critical value. So once you've calculated this test statistic here, we're going to compare it with the critical value you've retrieved over here, and using these two values we compare them with each other and see whether we should accept or reject H null. In this case, whether if we've not calculated these values, but if the test statistic is ever greater than the critical value, we reject the H null, which states that the data is independent, meaning that we need to state that there is sufficient evidence to support the alternative hypothesis. In this case, would say that there is sufficient evidence to state that the data is dependent on background music or not, and just vice versa if the test statistic is lesser than the critical value. So that pretty much concludes the type 1 question. Now we move on to type 2, the binomial distribution. This can be a bit more challenging since there's not a lot of questions that are asked based on these, but they're still just as easy. So yeah, typically there's a claim that states a condition and the probability of that condition to occur. So you'll be asked to test the claim to see whether it's true and see if the binomial distribution is a good fit for the data. So here's an example that I've put in from a paper. Apples are sold in bags of 5 based on previous experience. She claims that the probability of an apple weighing more than 100 grams is 0.35. Remember, 100 grams is not going to be used as a particular data value because it's just a condition. So the probability of success, as we call it in binomial distribution, which is p, is 0.35. So yeah, they're saying it's independent of other apples in the bag. And then you got this table over here which represents x and 0 1 2 3 4 5. So yes, this is basically all that we have here. And to calculate a goodness of fit test at 5% significance level and comment on Freya's claim. So when they say comment on Freya's claim, it basically means whether to accept or reject. Step 1 of every single test that we do is to state the hypotheses where applicable. So in this case, since we're using the binomial distribution as a model, okay, we're going to state that the bin bracket n comma p, where n is the total number of terms used, which in this case would be the sum of all this, or 150, comma 0.35, which is the probability of success or probability stated, and we have to state that this is a good fit to the data. Our alternative hypothesis H1 would state that it is not a good fit to data. It just contrasts with H null. Our step 2, calculate each individual binomial probability. This is really simple. It's just our principle of binomial distribution, where you have number of terms as 150. No, not the 150. In this case, since we're using individual binomial probability, our n becomes the maximum data value that x can obtain. In this case, it's 5. So we're going to use 5 and then our x value. So let's say we were calculating for 0, we'd get 5 combination 0, and now we have to multiply that with 0.35 to power of x. X is 0. Remember, p is the probability of success, which is 0.35, and we multiply that with 1 minus 0.35. I call this the probability of it being a fail, and we do n minus x, where n is 5 and x is 0. We do this calculation, we get 0.11603. Let's keep it to 5 decimal places. This is how you calculate the binomial probability. You do this for each and every single value here. It has to be done. And yeah, we'll get a binomial probability. However, it doesn't stop there, because this is where we go to step 3, where we have expected frequency. So if we were to calculate the expected frequency, it's obviously not 0.116 when the observed is 12. It would be somewhere near it. So what we do is multiply this binomial probability with the total frequency as shown, which is 150 over here. And as stated in the formula over here, our expected value or expected frequency would be 17.404. That's how we calculate the expected frequency. Once again, you got to repeat this for each and every single calculation. Maybe if the last data set, it may state that x is greater than or equal to 5. In that way, we can't really say that n is going to be 5. Instead, we'll have to use a different way of calculation. It is really simple to do this. In fact, there's only one principle that you need to know. The sum of all frequencies of the observed values will always be equal to the maximum frequency, which is 150. Similarly, the expected frequencies also always sum up to 150. So if we calculate individually and then we get a certain value, we subtract that with the total frequency you'll get for the final data set. May sound confusing in the end, but once you do practice questions, it will make sense. Okay, step 4. This is an optional one because it doesn't happen all the time, but there are questions that have obtained this. So for step 5 to be valid, which is this, you need to know that all expected frequencies must be greater than 5. How do we do this? Well, it's difficult because it's just tricky and it just really loses marks really easily. So if there is an expected frequency greater than 5, you have to combine the expected and observed frequency of 2 or more columns and then sum up the observed and expected frequency. So for example, let's say that our expected frequency here is, okay, let's just calculate that. So phi combination 4 times that with 0.35 to power 4 times that with 0.65 to power 1, which is 0.65 itself, and we times that with 150. So our expected here will be 7.312. 7.312 or 16. I think it was 16. Yeah, it's 16. Okay, now let's do the same for the other data set here over here. And how we do that is also the same method as we've done. So frequency times the binomial probability, which is 5 combination 5 times that with 0.35 to power 5, and we do this because, and then we get 0.7878, an extremely low value, which is definitely lower than 5, meaning that our calculation over here, step 5, cannot be valid. It cannot be valid if the value of your binomial probability is, if our expected frequency is less than 5. So what we do is that we combine the two columns here. So we combine this with this. We combine the two expected frequencies by just adding them. So we're going to have 7.3155 and we get 8.103. So this is our combined expected probability. Okay, so this is extremely important and it's a concept that's widely tested. And now you're going to get 0, 1, 2, 3, 4. You're going to get 1, 2, 3, and then you're going to say x greater than equal to 4. Okay, it's become an interval now. X greater than equal to 4, x lesser than equal to 5. So it's become an interval now, and our observed frequency will be 12 plus 4, which is 16. And now you can move on to this calculation here, where we plug in the limits n I equals 1 and the most famous equation used in chi-square test as shown above here. We're going to plug in this formula here and get degrees of freedom as well. That's used to sum, and yeah, this pretty much solves it. Critical value is the same way as we've calculated before, except in this case, if we have, let's say we have 6 terms, 1, 2, 3, 4, 5, 6, we need to combine the two of these. So now we are using only 5 values to obtain the test statistic. If we have 5 values, that means t minus 1 will be equal to 5 minus 1, which is 4, meaning that our degree of freedom is 4. And similarly, our p-value is 1 minus alpha, where alpha is your significance level test or significance level, and alpha will have to be represented in in decimal. So 1 minus 5%, which is 1 minus 0.05, which is equal to 0.95. We find the intersection of P and nu, which is degree of freedom, and we get the critical value. Next, the final step of every single test, regardless of which chapter it is in probability statistics, is to compare and conclude by saying that whether the test statistic is greater than the critical value or lesser than. And yeah, just apply this and you'll be able to get your conclusion. Now moving on to type 3, the Poisson distribution. It always states that an event, the claim will state that it follows a Poisson distribution. Otherwise you cannot perform this test. It always states that it forms a Poisson distribution. The mean number of let's say an event will be stated. So in this case, the mean number of breakages will be stated. This mean will be lambda. Okay, and it's explicitly stated here that the lambda over here is 2.5. See this? The mean number of breakages calculated from this sample is 2.5. So it's important that you recognize lambda equals 2.5. And now we have to plug in the value. H null, which is our null hypothesis, states that Poisson distribution is a good fit to data. Remember, we need to plug in lambda as 2.5. But since this is a general note, I'm not going to plug in any specific values. And H1 always contrasts H null, which is your null hypothesis. Your alternative hypothesis will state that the Poisson distribution is not a good fit to the data. This is quite prerequisite. It always stays like this. Step 2. Calculate expected frequencies based on your Poisson distribution. So this is the formula that you need to know. This is the Poisson distribution. Okay, E negative to the power of negative lambda times lambda to power r divided by r factorial. And we have to multiply this with our total frequency as we've done above. So earlier we've calculated binomial probability. This time we have to calculate the Poisson probability, and in the end we're going to multiply it with the frequency to get our expected frequency. And yeah, just plug in this for each and every single data value. Okay, now step 3. Combine two values if calculated frequencies lower than 5. Repeat the same step as shown in type 2 binomial distribution. Basically the combination of columns as stated before. It is extremely simple to perform. Step 4. To calculate the test statistic, it's extremely simple. Once again, we just do the most common formula used in all of this test. And the final step, no, not the final step, the critical value now needs to be calculated. And it's really a repetitive process, because it just always asks to state hypothesis, calculate expected frequency, find the test statistic, obtain critical value, compare and conclude. So you'll see that it follows a certain format and always follows this format. It never ever diverges from it. So just do note how the steps goes, and yeah, you'll be good for this. Okay, moving on to step 4, probability density functions. This you've obviously come across in continuous random variables, which is the first chapter that's introduced in further statistics. Good news, you don't need to know much of that. Actually, you don't need to know any of it. We just need to know principles of integration, and it's really simple. So questions normally ask us to calculate the expected frequency values first, in this case P and Q, and then they normally mark with variables as shown over here. And these expected values are basically prerequisite to the next question, because you need those two values here so that you can perform the goodness of fit test. Otherwise you're going to lose 7 marks, so it's quite expensive. So this note itself, this page itself would cover up both, because expected values are essential to calculate test statistic and therefore conclude. So first step, hypothesis. Extremely simple. PDF is a good model for the data. Our alternative hypothesis would just say the opposite, which means PDF is not a good model for data. As simple as can be. Next step, calculate expected frequencies. This is very simple. In fact, we just plug in values into the limit. So we normally are given just one PDF, but Cambridge is known to vary the questions a lot. So what we do is we need to see their intervals. Now since there's only one function, it's not much of a worry here. But let's say that there was a second function applying from 3 to 5. That means that your interval over here, let's say we were going to use this interval, you cannot apply it to the second function, because that function only applies from values of x in between 3 and 5, meaning that all these values here are invalid to the second function, means you must never use it. So be careful on the intervals and integrate only the right function. Alright, so how do we start this off? Firstly, we just need to integrate the function as shown over here. So in this case, 1 by 9x times 4 minus x. We need to integrate this and we'll get a certain value. Next, we need to plug in the limit of the interval. So I'm going to use an interval for better understanding. So now that we've integrated this, let's calculate this. All right. So 2 times. Okay, let's use an interval. Let's say we were trying to calculate the value of q. Since p is already given, it's not really essential to calculate, but let's find q. So our upper limit will always be b because b is greater than a. So yeah, let's plug in 2 times 1 squared. Remember, I'm using the integrated function here. Okay, just so that we don't get confused. 1 cubed divided by 3. Okay, and now we're going to minus that with 1 by 9 times, this is the distributive property of multiplication, and we're going to have the lower limit, which is 0.5 squared, and subtract that with 0.5 cubed divided by 3 and we get 29 by 216. This is the probability of it occurring. This is our PDF probability out of 1, but in this case the total number of observations made is 200, meaning we do our classic f times whatever probability we calculated. So in this case we need to multiply it with 200 and we get a fraction value 725 by 27 or 26.851. This is your value for q, and we're going to put it to 2 decimal places because p is also in 2 decimal places. So yeah, that's how we calculate our expected values. So once you get all the expected values, you're cleared to go to the next step, which is to calculate test statistic. And I'm pretty sure I've over explained this by now, but yeah, use the formula, obtain your test statistic. Just sum up every single one of them, you'll get your test statistic. Then you obtain the critical value as always. To calculate the degrees of freedom in this one, it's the same as we've done for the past 2 tests, where if you combine columns, that means t minus 1 will really become t minus 2. So let's say that expected frequency over here was 2.01. It means that it is not valid to pass on to this equation here because e value is less than 5. So what we do is combine these 2 columns, and there we have it. 1, 2, 3, 4, 5 columns used for values, meaning that our critical value would be adopting a degree of freedom of 5 minus 1, which is 4. It may be a bit tedious to explain it, but I'm sure you'll understand while writing the paper. So while getting the degrees of freedom, then we need to calculate the p-values, which is 1 minus alpha. In this case, alpha is 5%. Convert alpha to its decimal form, get p-values, find the intersect of the p and the degree of freedom, and you get your critical value. And the final step, as always, compare and conclude. Find the test statistic, the critical value. Once you've done both, compare them. If the test statistic is greater than critical value, you reject the null hypothesis. If it's lesser than, we accept the null hypothesis, and we have to state the conclusion. And these are conclusions as follows. So I hope you enjoyed this video and actually got some information to take back with you after watching this. I'm sure that some of this was valuable to you. Be sure to like, share and subscribe, and I'll see you in the next session.